Okay, so our next section here is talking about continuity. So we have our definition of continuity on a closed interval. So a function is continuous at x equals c if f of c exists. Okay, and so that's like saying I have a graph here and I need to have an actual filled in point somewhere at f of c. Then we have the limit as x approaches c of f of x exists. So, there's this difference we've talked about between f of x and the limit of f of x. I can have a limit even though I might have a hole in my graph. Limit is talking about what I'm approaching from the left and from the right. So I want to make sure that I have a limit that exists. And then I want to test and see if the limit that I've found that exists is the same as the y value that I found. So that's kind of our definition, and we're going to use that definition to prove if things are continuous or not, or to justify. Okay, so the first graph that we have here, we're just going to go through our steps. So we want to figure out, does f of c exist? Well, if we go to c and we look for the y value there, we have this closed point right here. So f of c does exist, and it's 2. The next thing we want to look for is the limit as x approaches c of f of x, and we want to see if that exists. And remember, limit is talking about as I get arbitrarily close from the left and I get arbitrarily close from the right, what is the value that I'm approaching? And in this case, that value is 3. So then the last thing that we need to check for is if those two things are equal to each other. And so for this one, f of c equals 2 does not equal the limit as x approaches c of f of x, which equals 3. So this is kind of the notation that we can write to justify our answer. So f of x is not continuous at x equals c. Okay, so this part right here, this was the justification of our discontinuity, okay? And so we call this a removable discontinuity. Because we could change the function to plug the hole. Okay, so we call this a removable discontinuity. So when we have this hole, it's just like a part of the graph has been removed, and we could fill that hole back in if we wanted to. All right, so next one. So same graph, the only difference is we've removed the point. So if we look at this one, first thing we want to test for is what f of c is and if that exists. So in this particular case, we have no f of c. There's just a hole there, there's no point. So f of c is undefined. So we'll just say f of x is not continuous at x equals c because f of c is undefined. So you need to get used to justifying things in words. And this would also be a removable discontinuity. All right, so next one. So same thing, we're going to do f of c. And in this case, f of c is 1.5. We'll do the limit as x approaches c. Now, when we check our limit here, once again, we're thinking of this fact where I'm getting arbitrarily close here to my c, and this side looks like it's approaching 4. This other side, as I'm getting close to my c, looks like it's approaching 1.5. So the limit there does not exist because it's approaching different things from the left and from the right. So this does not exist. And we'll say because the limit as x approaches c from the left, okay? So this little negative sign, that's saying from the left side, okay? And so that negative is implying we're looking at the limit coming from the left side, okay? And that is going to be equal to 4. And that does not equal the right side limit. Okay, so that little plus sign is saying the limit approaching from the right side. So this right side limit, as we approach from the right, that's approaching 1.5. And I should have put f of x here. Okay, so those do not equal each other. So we're going to say f of x is not continuous at x equals c because the limit as x approaches c of f of x does not exist. So we really want to justify that well. This is what we call a jump discontinuity. So this is that situation where if I have to travel on my graph and then I have to jump to get to, so I have to jump from here to here, that's what we're referring to when we say jump discontinuity. All right, next graph here. So f of c is going to be 1, because that's this point here. Then we have the limit as x approaches c of f of x. Now, this is a little complicated because our textbook says that the limit at c here does not exist. Okay, so textbook says that does not exist. The reality is, though, that the graph is going to the same place from the left and the right. it's just that place that it's going is infinity, which isn't like a real number. So I'm going to put infinity here. And I know in the last lesson that we did, we were saying that that didn't exist. So we'll have a conversation about what we feel like should be the answer we should put. But I'm going to have to do some research on what the AP test is going to want, or if you're going to be asked that, or anything like that. So we're going to say then f of x is not continuous at x equals c because f of c equals 1 does not equal the limit as x approaches c and we'll say that this is an infinite discontinuity. Okay, so it's going to infinity, so an infinite discontinuity. Okay, so this next one, when we try to figure out f of c, there is no point at f of c because there's an asymptote there. So f of c is undefined. The limit does not exist. And the reason that it doesn't exist is we have this graph going infinitely up and a graph going infinitely down. The limits are approaching different things, so it wouldn't exist. So we'll say f of x is not continuous at x equals c f of c is undefined or you could say because the limit as x approaches c of f of x does not exist. So either of those will work. Okay, so we're going to discuss the continuity on this one. So we have the function f of x equals 1 over x, and this is the picture. And so we want to discuss where it's continuous. And so if we think about this, I'm continuous here, but I have this asymptote here where I'm not continuous. So we'll say f of x is continuous over the interval negative infinity to 0. Okay, so that's this graph right here. And we're talking about x values when we do intervals, so negative infinity to 0. And the reason that we have these parentheses, those are not inclusive. And remember, brackets would include those numbers. So like infinity is a number we can never touch, so we're not going to put a bracket ever within an infinity. And then we have this asymptote at 0. So 0 is not included in this domain, so we're going to put a parenthesis at 0. And then we'll say union 0 to positive infinity. So this is the domain, and it actually ends up being where it's continuous as well. And we're always using x values here. So these are x values. We could also say over the set of all real numbers where x does not equal 0. So that's another way that we could write that same thing. All right, so we're going to discuss the continuity here. So we have a function. We have x squared minus 1 over x minus 1. So one thing I notice is because this is rational, if I plug a certain number into the bottom, it's going to make it undefined. And so what we can do is we know that there's going to be some type of either hole or asymptote there. And so what we can test is if I can factor this and cancel that bottom somehow, that tells me a lot about what type of discontinuity it is. So this is a difference of squares. So we'll have x plus 1, x minus 1. So these actually will cancel, and I'll get just x plus 1. So what that tells me is that this is a removable discontinuity for this function. I can factor and I can get rid of that. So there's just going to be a hole in the graph there, not an asymptote. So x cannot equal 1. So if we graph what this looks like, so it's the line x plus 1, and we know when x is 1, we're going to have a hole there. So the graph's going to look like that. So this is a removable discontinuity. So our domain here, if you're looking at it, domain is going to be all real numbers except x cannot be 1. It is continuous over the interval negative infinity to 1, union 1 to infinity. And so that just means everything from negative infinity up to 1, not including 1, everything from 1 to infinity, not including 1. So we could say, or everywhere except x equals 1. So these are just different ways to describe the same thing. Or we could say over the domain of g of x all real numbers except where x is 1. All right, so if we're looking at this graph and we're thinking, where's this continuous? We're just going to talk about the intervals where it is continuous, okay? So if we write this down, we have this right here. So that interval is going to be negative infinity to a. A is not included there. Union. Then if we look here, I have these closed dots on each end of this. So this is going to actually be a bracket A to B. which is also a bracket because it's a closed circle there. And then this last interval that we have is this one. So we'll say union b to infinity. All right, then we're going to go into continuity on a closed interval. A function is continuous over the interval AB if f of x is continuous on AB. Okay, so basically we have a function. So let's say we have something like this. Okay, so if we have A and B, so we want to be continuous over this whole interval in between here. Okay, and then it also wants to say the limit as x approaches A from the right. Okay, so as we're approaching A from the right, so the limit at this point, okay, equals the actual f of A there. And then this other one is going to say the limit as x approaches B from the left. Okay, so as we're approaching B from the left, we want to see that the point, that end point, is the same, the limit of that endpoint is the same as the actual f of B. Okay, so let's discuss the continuity of this. We have f of x equals the square root of 1 minus x squared. So that's going to look like this. Okay, so we have -1 and 1. So the domain for this is going to be this closed interval -1 to 1 at all points on -1 to 1. So the continuity, it is continuous. And we could prove that using the theorems that we have talked about before. So then we also want to discuss, is it continuous over the whole closed interval? Okay, so we also want to add, moreover, because, so we want to see the limit as x approaches -1 from the right. Okay, so we want to check our graph as we approach -1 from the right. What is that value that we're approaching? It's 0. And we want to check that that is the actual value of f of -1. And it is. So that's the same thing as f of -1. And we also want to check that the limit as x approaches 1 from the left. So as we approach this other endpoint from the left side, the limit there is also 0. And we want to make sure that that is the same as the actual f of x there. And it is. So f of 1 is 0, and the limit there is also 0. So because of that, you can conclude f is continuous on the closed interval. All right, next thing is if we are given h of x Okay, so what we want to find out here is find a so that h of x is continuous everywhere. So, and if we look at this graph here, so if we look at this right here, we have this x minus 2 on the bottom. And so what's going to happen there is we actually have a removable discontinuity there. And we can't use 2. And so what we want to find out is we want to find out what is the y value at a, or what is this y value that is a, that if we add that to this piecewise function, suddenly that removable discontinuity is filled in. So this part right here is filling the hole. So let's explore that a little bit. So if I have okay, so I know that the bottom of this is going to be undefined when I have 2. So let's say if we can factor the top of this. So factors of 2 that subtract to 1 are going to be 2 and 1. Highest number gets this sign, so that's negative, and they're going to be different, so x plus 1. So these are going to cancel, and I get x plus 1. So what I want to figure out is I want to figure out what is that y value at 2. So what's my limit there? And then that's going to be my a value. So if I take 2 and I plug it in to this x plus 1, I get 3. So if I graphed this function, I would have a hole at the point 2, 3. And so the whole point of adding this right here is to plug that hole. So if a is equal to 3, then suddenly that graph is not discontinuous anymore because it has become a piecewise function.